Welcome to this explainer. Today, we are embarking on a really incredible journey. We're going from the absolutely invisible, microscopic world of atoms all the way out to the grand master map of, well, absolutely everything around us. Whether it's the device you're using right now, the water you're drinking, or literally the stars in the sky, we are going to break down the fundamental rules of physical reality.
All right, let's just dive right into it with a number 118. Now, it sounds small, right? But this single, incredible number represents absolutely every known substance in the entire universe. Just pause and think about that for a second. The boundless, infinite diversity of matter that we experience every single day, from the air we breathe to the deepest oceans to the most complex technology we build, every single bit of it comes down to just 118 fundamental ingredients.
So here's our roadmap for today. First, we'll meet the atom, then check out the ultimate organizer, decode some chemical symbols, and finally look at metals versus nonmetals. Kicking things off with Section 1, Meet the Atom, the invisible foundation of matter. Okay, so to really wrap our heads around the massive variety of stuff in the universe, we kind of need to get our definitions straight. An atom is the absolute fundamental unit of matter. It's the smallest piece of the puzzle you can possibly have. But when you get a pure substance that is made entirely out of just one specific kind of atom, we call that an element. It's an absolutely crucial distinction. Think of it like this. The atom is the individual brick, and the element is a solid wall made entirely out of that exact same type of brick with zero other stuff mixed in. And it's so fascinating to see how these atoms actually behave out in the wild. For instance, you've got free-floating neon atoms just zipping around completely unattached, which is super typical for a gas. Then you've got oxygen particles that like to pair tightly together. Or take sulfur. 8 of its atoms will actually join up into this really distinctive ring shape. And then, unlike those free-floating gases, atoms in metals like gold pack themselves closely together into a really rigid, tight, geometric structure. Moving right along to Section 2, the ultimate organizer, making sense of the chemical chaos. Remember those 118 elements we talked about? Well, there's a pretty wild division here. Only 94 of those actually occur naturally in the universe. That means the remaining 24 elements were entirely created by humans. Think about that. Scientists literally synthesized 24 brand new elements in laboratories. We didn't just discover the building blocks of the universe, we actually cracked the code and learned how to build entirely new ones ourselves. But as you can probably guess, keeping track of 118 totally different building blocks, some natural, some literally built in a lab, could turn into absolute chaos in a heartbeat. So to arrange all this matter, scientists developed a massive, highly organized library. We know it, of course, as the periodic table. And it's not just a basic list, it is a meticulously designed grid, where a single glance can tell a scientist almost everything they need to know about a specific element. Now, to actually read this map without getting totally lost, you gotta know its geography. The table itself is strictly organized in 2 very distinct directions. The vertical columns running up and down are called groups, and the horizontal rows running left to right across the table, those are called periods. Pinning down this distinction is basically the master key to unlocking how the whole system works. And here's what's actually super fascinating about those horizontal rows, the periods. The table is definitely not random. As you read across each period from left to right, the atoms systematically increase in mass. It starts with hydrogen, which has the absolute smallest mass, and steps up to slightly heavier helium, then lithium, and so on, straight across the row. It's just this incredibly elegant way to bring strict mathematical order to the physical world. That brings us to Section 3, Decoding Chemical Symbols, the secret shorthand of science. Look, scientists do not have the time to write out full element names every single time they do an experiment. So elements are given symbols as a really handy shorthands. Decoding it works exactly like a logic puzzle, following 3 main rules. First, the easy one. It's just the first letter of the English name, like O for oxygen or H for hydrogen. But what if that letter is already taken? Well, Rule 2, use the first letter plus another letter from the name, like He for helium or Li for lithium. But Rule 3 is where it gets really fun and, honestly, kind of wild. Some symbols are pulled from entirely different ancient languages. For example, the symbol for sodium is Na. Why? Because it comes from the old Latin word natrium. Same goes for potassium, which uses the symbol K. It's like a fantastic little hidden history lesson baked right into the science. But wait, if you're going to write these scientific symbols out yourself, there is literally zero room for creativity. You absolutely must remember the golden rule of formatting. The first letter of a chemical symbol is always, always uppercase. And if there is a second letter, it is always, always lowercase. Writing each E for helium with two capital letters is scientifically totally incorrect. It must be a capital H and a lowercase e. This strict standardization is a real lifesaver. It prevents massive confusion and potentially dangerous accidents when reading complex chemical formulas. What's so cool is that these tiny symbols map directly onto the tangible, messy reality of matter. We're talking about silvery aluminum dust perfectly matching up with its symbol Al, or rough, chunky pieces of zinc denoted by Zn. You have bromine, which is this deep, reddish-brown liquid, matched with Br. Then there are dark, spherical pellets of lead for Pb and fine copper shavings for Cu. This shorthand system perfectly bridges the gap between high-level scientific theory and the physical stuff you can hold in your hand. And finally, Section 4, Metals versus Nonmetals, Categorizing the Elements. Honestly, one of the most genius aspects of the periodic table is how it clusters things together visually. Elements with similar properties are deliberately grouped together. They are basically sorted into distinct, color-coded neighborhoods. Metals like lithium and sodium are cleanly grouped together in one zone, while nonmetals like oxygen and carbon sit safely in another. By simply knowing an element's geographic location on this map, you instantly know a tremendous amount about how it behaves, what it looks like, and what physical properties it has. It's a total game changer. So as we wrap up this explainer, I want to leave you with kind of a mind-bending thought. The periodic table, it isn't a finished document, it's a living map. Knowing that human beings have already successfully synthesized 24 entirely new elements in a lab, we know for a fact that the map can still grow. So what do you think the yet undiscovered, uncreated element 119 will actually look like? Will it be a heavy metal? Will it exist for just a fraction of a millisecond before vanishing? And perhaps most importantly, what secret symbol will we assign to it to mark our very next great scientific achievement? Thanks for hanging out with me on this journey through the building blocks of our universe. Keep questioning and definitely keep exploring.